Good morning, good afternoon, good evening. I'm Ian Tabor, or better known as Mintynet. Thank you again to Grimm for having me at your conference for a second time with my presentation titled Value Pasta Auto, How I Built It and Saved $28,000. First things first, who am I? You could say I'm the ultimate car hacker. Built this kit car 17 years ago now. It's a Tiger Supercat and it only has 3 ECUs, of which 2 of them I built myself. It's basically a Ford Focus engine and Ford Sierra running gear. Doesn't weigh a lot, rear-wheel drive, great fun to drive. However, the British weather and life gets in the way, so I don't get to drive it as much as I'd like to. Anyway, on to my car hacking credentials. Here are the details of my previous presentations and events related to car hacking. You may know of me due to me building my car in a box PD0, which is most of the electronics from a 2014 Peugeot 208. I built it at the end of 2018 after seeing Grimm's 3PO at DEF CON Car Hacking Village that year. My car in a box thinks it's a fully working vehicle, which I previously presented about at GRIMMCon 1 and how I now run the car hacking village in the UK. I take my car in a box to events across the UK, and I have once been to Amsterdam, which was fun getting through customs. Ask me about it sometime. 2020 was meant to be the tour of Europe year, where I was going to visit Dublin, Brussels and Stuttgart. However, COVID and Brexit got in the way, but through the use of technology, virtual car hacking village happened for a few events, and I managed to present at some other events too, which I may not have done if COVID hadn't have happened. However, I have been invited globally to take my car in a box to numerous locations, including India, Australia, Philippines, Singapore and Brazil. My car in a box is portable, but it's not that portable. Onto the car in a case, Pasta. What is Pasta? Pasta was originally released at Black Hat Europe 2018 and was developed by Toyota Info Technology Center. I have actually seen it in person in September 2019, but I didn't get a chance to play with it. Bit of a shame. So Pasta, portable automotive security test bed with adaptability. Pasta is designed and developed with a following philosophy. It is open. It must be based on non-proprietary technologies. Adaptable. Users should be able to rewrite the firmware of the ECUs, redesign the architecture, and connect their own devices, for example. Safe. There should be no real actuators. It can avoid incidents, such as wheels, brakes, and windows should be realized via simulator, not using the real things. Finally, it must be portable. The platform is preferred to be small and portable so that users can study, research, and hack it anyway. Here is a picture of Pasta. There is a link at the bottom there that gives you the full details of their product. I will go into some highlights. If you want any more information, look at that link and watch some of the presentations that they have done at various events around the globe. The case in question is probably about the same size as the average gentleman's briefcase, shall we say. Top half of the case is inputs and outputs. There are 3 screens and a load of buttons. The bottom half of the case, there are 4 ECUs. 3 of them are body, chassis and powertrain. The 4th one is the gateway that joins them all together. The gateway ECU has a 4th CAN bus connected to it via the OBD2 port, which on that picture is not shown because it's in the bottom right hand corner. I will go over some highlights of how I believe it fits together, but I will not go over the full details. So Pasta is open source. Within that GitHub repository, there is the firmware for the ECUs, there is the hardware and software spec, there is the schematics for the ECU, there are some CAN definition files. One thing they do not publish within there is any great detail on how the top half of the case connects to the bottom half. Okay, we can see that there are 3 screens, powertrain, body and chassis going to the 3 ECUs. If you read the document Pasta 1.0 ECU hardware software spec version 1.0e, it says that the I/O is connected via serial using SCI 0. That can be confirmed by looking at the closely at the diagram. The pins on the left here are where the I/O SCI 0 is. So I would assume that it connects, but there's no great detail. However, looking at the CAN definition files, all the switches and potentiometers across here initiate messages from the chassis ECU. So that is where they will be connected online. So this white box ECU, what is it? There is a picture of it. big black chip in the middle there is a Renesas RX63N processor. It has 2 meg flash, 256K RAM. Internally, there is a real-time clock, an Ethernet MAC, USB 2.0, 3x CAN 2.0, I2C, SCI, SPI, and probably some 3-letter acronyms I've missed out. When I first started looking in 2020, this chip was available, about $26 each. However, it's no longer available. There is a similar replacement chip. It's $15 each, but there is a minimum order quantity of 480, which sums up to be $7,200 just in processors before you start. So the white box ECU needs 4 CAN buses. It has 3 internally. The additional one is provided via an external CAN controller, the microchip MCP2515. In the middle there you can see 4 CAN transceivers. They are the NXP TJA 1050s. They can run up to 1 megabits CAN bus. The yellow connector there is RS232. JTAG is there. Battery there for the real-time clock. And on the reverse, I believe, is a micro SD card for future possible expansion. So the CAN definition file. Here is a abstract of that CAN definition file from within that GitHub repository. It shows the source and destination of CAN messages, the frequency of the message being sent, and finally how the data is encoded in the data bytes of that CAN message. So if we look at the top row in the pinkish, we have a break operation indicator. Its source is the chassis ECU. Its execution is the powertrain ECU. It has an ID in decimal of 26. It has an ID in hex of 01A. It is repeated every 10 milliseconds. It's got the length of 2 data bytes. Its off or minimum is 0. Its on or maximum is 1023, which means it's a 10-bit number. And its unit is percent. So finally here is a calculation that tells you 256 times A plus B, all divided by 1023, gives you that percentage. On the next slide, I will summarize this entire document rather than you having to read it all. Here it shows you that the chassis bus is sending 810 messages per second. The powertrain bus is sending 668 messages per second, and the body bus is sending 380 messages per second, not bus ECU. The total number of messages going into the gateway ECU is therefore 1,858. However, it also has to send those 1,858 messages back out again to the other ECUs on the other side. So the CAN gateway ECU is actually processing 3,716 messages per second. So onto the inputs and outputs. As I said previously, there are 3 LCDs that show for the powertrain, body and chassis ECU. They show outputs from the ECU itself. And then there's switches underneath. The following, there are 3 potentiometers, brake, accelerator and steering, 2 rotary encoders, headlight and front washer wiper, 3 toggle switches, which is shift position, indicator or blinker, rear washer wiper. There are 8 push switches, 4 of which are for the windows up and down, and the final 4 also have indicators, which is for the ignition, door locks, handbrake and hazard lights. Finally, at the top of the case itself, you will see a small USB Bluetooth dongle that is used for the Bluetooth connected car that can be controlled via passenger itself. Anyway, enough of the Toyota version. We go on to Value Pastor Auto. Software is written within the Arduino IDE. First thing I had to do was work out if the microcontroller and or the library in use would be able to send enough messages quick enough. The MCP2515 library I was using, still am using, is one from Corey J. Fowler, link being there. What I did was wrote a script for my NanoCAN device to send as many CAN messages as it could for 5 seconds, and then take an average number of the count that was created from those 5 seconds and analyze that using a logic analyzer. A single 8-byte CAN message will take about 240 microseconds on the wire. at 500 kilobits per second CAN bus, which gives a theoretical maximum for that bus speed of just over 4,000 messages per second. Here is the first bit of analysis on the 2016 library. Managed to get through about 848 messages per second. Looking at the way the library works and the data sheet, the first command here is read a register to check if the buffer is empty. I then write the 8 bytes of data into the controller. I then write another byte in from the data length. I then write 4 bytes in for the header information of the CAN message. I then finally write a single bit into a register that says transmit the message. On the wire, the message then transmits. I then check to see whether that message has been sent, and everything starts again. As you can see, there is a fixed period here between this command and the result, this command, the result, this command, the result, this command, the result. This was actually written into the library itself of a 250 microsecond delay, so I think we can do things better. The later version of the library itself, the 2017 version, I could manage to get 2,606 messages per second because of removing those delays. Again, we're using the same method of check a register, write some data, write some more data, write some more data, send the message. It then does some polling to see whether the message is sent. Finally, when the message is sent, it then allows it to send the next message. This time the delays have been removed. We're just waiting for the polling to happen. However, looking at the data sheet for the CAN controller itself, there is a function that allows you to write all of the data into our transmit buffer 0 in one go. So I modified the library itself to actually do this in one go. As you can see here, there is the command that sends some data to the CAN controller. There's a single command that says send the data. We then poll it a load of times, find out it's sent, and then reset the bit in the interrupt function to say the message has been sent, and everything starts again. This version of the library managed to send 3,049 messages per second. If you can see here, there's a minor delay between the writing of the data in and actually the sending. This is due to the digital write function being used in the Arduino IDE, which takes about 8 to 10 microseconds, which means you can actually make it even quicker. This is the final version of the library that I used, in that I used direct port manipulation and managed to get it down to 3,309 messages per second. As you can see down the bottom here, write the data in, almost immediately tell it to transmit, and then it transmits. So that's a bit better than the 848 messages per second, and the direct port manipulation only takes 2 microseconds. So onto the microcontroller. The original plan was to try and use an Arduino Mega 2560, which has the Atmega 2560 16 megahertz CPU, but has no CAN controller on board. This will potentially cause issues because you're forever waiting for the SPI bus to get the data out of the controller, or forever polling the controller. So that was sort of parked. I then looked at the Itsy M4 via Adafruit. It has the ATSAM D51 at 120 megahertz. Again, it has no CAN controllers, so would have to have 4 external SPI-based controllers. Again, it would be forever waiting to see whether those SPI controllers are actually got any data. So finally found the Teensy 4.0, which is an ARM Cortex M7 at 600 megahertz. Can be overclocked to over a gigahertz if you add some heat sinks. The good thing about this microcontroller, it has 2 CAN 2.0 controllers on board and 1 CAN FD compliant controller. Looking at the benchmark stats for those 3 different ECUs, or microcontrollers, shall we say, the Arduino Mega has a value of 7. The Metro M4 has a value of 215, which is about 30 times faster. And then the Teensy 4 has a value of 2,314, which means the Teensy is about 300 times faster than the Mega. It's a pretty good little chip in the scheme of things. On to the hardware, the PCBs. Here is the version 0 of my PCB from 2020. There is actually a mistake on it. Here you can probably see it at the bottom there. There is an LED, single surface mount one. It should have been a NeoPixel, but I put the footprint on backwards, so couldn't use it. Here we have the Teensy4 on the left, battery connector for the real-time clock, the external CAN controller here, and clock. We then have 4 CAN transceivers, third one down being slightly different in that it's a CAN FD transceiver. And then we have the automotive grade connectors on either side. The right hand side is CAN and power. The left hand side is inputs and outputs. I did actually create a version 1.1 of the PCB to fix the NeoPixel footprint, but I never sent it to fabrication. I then created a version 1.2, which has some extra additional interrupts on the CAN controller to allow you to trigger on transmit or receive buffers directly, as opposed to using SPI interrupts or SPI control. Again, it looks almost identical to this. The other one, the only one out of the 4 is actually 1.2, is the gateway one, because that's the only one that needs to actually use all 4 of the CAN controllers. Here is the I/O board. The I/O function is provided via 2 MCP23017 I/O expander boards, each of which has 16 inputs or outputs, which you can see at the top there. You've got 2 rows of 8 above the two chips. At the bottom there, you've got some power and ground. You then have the 4 analog inputs, the Nextion serial, which is serial 5 within the Teensy. On the powertrain ECU itself, analog 2 and analog 3 is used for serial 4. And again, we have a 20-pin automotive grade connector to connect it back to the ECU itself. It's a different one to the ECU, in that it's keyed slightly differently. It's black rather than grey, so you can't mess it up and get it the wrong way around. Here is what it looks like within the roof. It's a bit messy. I really don't want to unplug it, so that's all you're going to get regarding pictures. So again, onto the inputs and outputs. There are 3 3.5-inch Nextion human machine interface screens. I'll go into a bit detail on that. Those are individually connected to the 3 ECUs, powertrain, body, and chassis. We then have most of the switches on there are connected to the chassis ECU. There are 3 potentiometers, again for brake, accelerator, steering. There is a little steering wheel there. It came off of the keyring. There are 2 rotary encoders, including push for front lights and flash, and front wiper and washer. There are 5 toggle switches, 2 for the windows, 1 for indicator, 1 for gear indicator, and 1 for the rear wiper and washer. There are 6 push switches, you can see, hazards, lock and horn, and 2 additional push switches that include 2 indicators for parking, brake and ignition. In the bottom left-hand corner, you can also see another rotor encoder and potentiometer, which is connected to the powertrain ECU, which is used for the mode functions to connect the box itself to the Bluetooth car, etc. There is a Bluetooth BT05 on the powertrain ECU. You can't see it at the moment because it's tucked down the left-hand side somewhere. There is a bit of black acrylic underneath it, which holds it all together, which was manually cut in my kitchen. Don't tell the wife. It actually needs to be replaced, but I personally like it because it shows that it was sort of hand built. So on to what it looks like. Here is the case in the closed variety. It's quite small, it's quite portable, doesn't really weigh a lot. It's a lot lighter than my car in a box. Here is the case open. As you can see at the bottom there, there are the 4 ECUs. I'm actually using PCBs for the front and rear plate, so I can get them cut out correctly, as opposed to me using, again, a file and a drill on the kitchen. Don't tell the missus. Onto a close-up of the top half. Again, you can see the top half acrylic. It is wedged in with a bit of bubble wrap, which stops it falling out when you open the lid. However, we are where we are. Onto the bottom half of the case. So in the bottom half, you've got the 4 ECUs across the middle there. In the bottom right hand corner, you've got a 12 volt to 5 volt power supply. The 12 volt also feeds the OBD2 port to give it power. Bottom left hand corner there, you have a 6-way fuse box. Those are actually connected behind together, but it allows you to jumper into each of the 3 buses for powertrain, chassis or body. They actually are connected, the jumper wires are connected to pins 3 and 11 on the OBD2 port. The standard 6 and 14 is connected to the gateway ECU's OBD2 port as well. Top half of the case looks like this if you accidentally open it when the bubble wrap isn't wedged in. That bit of card holds it all together. Behind that bit of card is a bit of a spaghetti mess. I'll use some of my other little PCBs that I've broken, misconfigured, etc. as sort of holders to hold it all together. It works quite well. The case in question is 255 by 345 by 115 millimeters. For you in inches, it's about 10 by 14 by 5, I think. So the code, as I said previously, I started on the repetitive sending of the dummy data using timer-based interrupts to make sure I could send that 810 messages per second. Once the IO PCBs arrived, I had to then write the code to interact with the inputs and the Nextion displays. Initially, there were 4 separate bits of code, each for the 4 ECUs. However, I have subsequently aggregated them into a single code sketch. Within my GitHub repository, there are the original single ECU codes, but I offer no warranty on them at all. I have no warranty on the whole solution either. So the Nextion human machine interfaces, they are serial-based displays, which send serial commands back and forward. You basically program it with something to display on this IDE. You can then make things visible or not visible. You can make values show up, etc. Make dials change by sending data. You can also run a simulator to show what would happen on one of their boards. In the left-hand side there, it says page 0. That basically tells it to turn to page 0. In the middle, you can see the result of that command, which goes back to the microcontroller or the simulator. Those characters, bytes there, basically tell it is now at page 0, so the microcontroller knows those things are. Next screen is a little demo. Start on page 1, I think it is, and then paste something in that says go to page 0, which does my little intro screen, flashes through all the lights, etc., opens and closes the windows, and then sends a thing saying the page is done. It then puts the brake lights on. I then paste in again, turn off the brake lights, and then click around the screen to show you there are hot areas on the screen for the doors, bonnet, and trunk. That allows you to send data back to the ECU saying someone's clicked on something, so that it can do something with that. Works quite well. They are pretty cheap. I'll go into costs in a minute. Next part of the solution is the little Arduino based car. I bought this from Amazon for about £50, I think it is. By default, it can be used using Bluetooth, infrared, ultrasonic detection, or line following. I had to modify the code that controls the lights to be the same as the body ECU, so that when the lights come on the body, the lights would come on the car correctly. It's like indicators, side lights, headlights, main beam. I also had to change the gateway code to allow some of those messages to go to the powertrain ECU, because normally the powertrain ECU wouldn't see the details of the horn, etc. There is some logic within the powertrain ECU that tells the car how fast to drive or how fast not to drive. It basically calculates a value depending on the accelerator pedal, the brake pedal, and the handbrake status, and the engine on status, and then sends it over Bluetooth to the car. So onto a bit of a demo. So here's a demo. First turn it on, goes through its initialization sequence. You can see the little red flashing light in the corner that shows the Bluetooth is working. First turn the ignition on by pressing the ignition on button, which works fine. Then take the handbrake off on the left. There is an issue here with switch bounce, but it does work most of the time. So the handbrake is off. I then turn it around to mode B, which means the Bluetooth car is connected. I can then increase and decrease the accelerator. You can see the accelerator going up and down on the rev counter. Brake you can see changing. Indicators flashing on both the chassis and body ECU, both for right and left. We then change gear from park, reverse, neutral, drive. And now what I am doing is going to lower the right-hand window, lower the left-hand window. Try and lock the left-hand door, lock the right-hand door. Again, we're having switch bounce issues. Doesn't really matter most of the time. That's that. Now we go on to a demo of some hacking happening. What I have connected to the OBD2 port and also the chassis ECU is a NanoCan device which is spoofing hazards on, flashlight, flash the headlights, fuel gauge at 40%, coolant temperature max, steering at full right, and accelerator at 10%. If you watch both the chassis and body ECU, you can see things happen when those messages get injected. So here we go, lights are flashing, indicators are on, fuel and temperature gauge is going nuts, and the accelerator is going nuts. As you can see, it's stuck on with the hazards and the lights. You basically have to interact with the inputs, otherwise it will not reset it because it looks for a change of the inputs normally. That's that demo done. Here's another little demo with my little friend Biggie, the mascot of the car hacking village. Hello! He's now going to be driving on full left-hand steering, and the same messages are going to be injected again: full right-hand lock, change of accelerator speed, flashlight, etc. So we're going around full left. I'm going to inject the full right-hand lock, which is causing it to stutter. Again, stuttering again. He's getting a bit dizzy. The hacking has stopped. Now I'm going to turn around. And lights on. And whee! Disappear into the sunset. So finally, how much did it cost me? So costs here shown are from mid-2020 and do not include postage and packing. The ECU boards themselves, creating my own custom PCBs, getting all the different parts. The teensy itself is about £20. They cost about £50 each in total, and there is 4 of them, so that's £200. The I/O boards cost about £25 each. There are 2 of them for the chassis and powertrain. The body ECU doesn't require an I/O board, so it didn't need one connecting. It just needed the Nextion display connecting. So that's a total of £50. The 3.5 inch Nextion displays are about £30 each. They are pretty good. They go all the way up to, I believe, 10, 12 inches in size, with quite a lot more resolution. So that's a total of £90. The case, the car, the cabling, the switches, and all of the bits on the inside come to about a total of £160. So in total, it costs me £500 to build, which at about today's exchange rate, that's $800. Toyota Pasta Auto, currently, if you want to purchase it, is $26,780. So I built it and saved $25,980. So maybe I should have changed the name of my presentation to Value Pasta Auto, how I built it and saved $25,980. Finally, I'd like to say thank you to my missus for putting up with my crap, and while I've been building this and PDO. I'd like to say thank you to Terry Ip. He used his 3D printer to print the surrounds for the Nextion displays to allow me to put them into the case. I'd also like to say thank you for the Grim Cyber team for allowing me to be here and for their previous help with my car in a box. I have actually sent BitBane a couple of the different PCBs if he wants to try and build one of the ECUs himself, but I don't think he has. But again, thank you. I will be around for the next 15-20 minutes on Discord. If you have any questions, if you want any more information, contact me via the methods at the bottom there. And there is a link to my GitHub for all the files relating to Value Pasta Auto. Thank you very much and good night.